Hello, advanced algebra students, and welcome back to another video lesson. Today we're going to continue working on our systems of inequalities, but begin an introduction to what is called and known as linear programming. So we're still taking these concepts that we've learned, properties of systems of inequalities. Can you solve real-world problems using linear programming? And can you interpret what the solutions in the context of a situation modeled and decide if they're reasonable? Right? So we're taking these story problems. We're going to use a system of inequalities, use a process known as linear programming to kind of help us understand what's happening. So I'm going to give you a warning. This is a big example out of your packet coming up. It's an introduction to linear programming and what that means. So follow along closely. We are working on page 13 out of your packet. It's called the Built Right Furniture Company, who makes wooden desks and chairs. Carpenters and finishers work on each item. On average, the carpenters spend 4 hours working on each chair and 8 hours on each desk. There are enough carpenters for up to 8,000 worker hours per week. The finishers spend about 2 hours on each chair, 1 hour on each desk. There are enough finishers for a maximum of 1,300 worker hours per week, given these restraints. Find the feasible region for the number of chairs and desks that can be made. Whew. A lot of information there, okay? But let's maybe focus on this last part. Often it's the last sentence or question, right, that guides us into where to get started. Find the feasible region for the number of chairs and desks that can be made each week. All right, so that's what we're looking for in the end. So I'm going to say that chairs is going to equal something. And then I'm going to say that D is going to equal relative to the desks. And I'm going to type the next part just so it's not as sloppy, I guess, maybe. So D is going to be the number of chairs made per week. So that's what we're going to let C equal. And then hopefully you can pick up on the fact that D is going to represent the number of desks that are going to be made per week. So C and D, okay? Now, the next part that will help us over here is to make sure that we are filling in this table. So we're making desks, we're making chairs. So we're going to let's just use a different color here, Mr. G. We're going to let this one be our chairs for C. How many carpentry hours does it take to make a chair? Well, carpenters spend 4 hours working on a chair. And carpenters spend 8 hours on a desk. Why is the 8,000 down here? Well, that's the total that we have to work with, right? Maximum hours to work with. So the total max. If this column represents carpenters, we're going to let this column then represent our finishers. The people that are going to apply perhaps a stain or something, to each of these. Okay, and the finishers spend 2 hours on a chair, so 2 hours on a chair, and 1 hour on each desk. The maximum we have for finishers is 1,300. So 1,300. We have an extra column in this problem that we don't really necessarily need, which is okay. So that's kind of where we're starting, trying to gather the information and figure out where we're going to go, right? The total max being 8,000 for carpentry hours, the total max for 1,300 being for finishers. All right. Now what we need to try and do is translate that information into inequalities, or what we call the constraints of the problem. And so I'm just going to copy this and bring it over to that next slide so that we have the information with us right over here. And we're going to try and take this information and turn it into the inequalities or the constraints. Okay. So each one of these columns is going to help us write a constraint. The first column is 4 hours times every chair plus 8 hours times every desk is going to be compared to 8,000. Can our hours work? Remember, these are the hours over here. The number of chairs that we build, can they be equal to 8,000? Certainly, because that's the maximum we have, but it can't go over that. So 4C plus 8D has to be less than or equal to 8,000. Equality 2. Inequality number 2 comes from the finishers. 2 hours for every chair plus 1 hour for every desk has to be less than or equal to 1,300. Right? We can't go over 1,300 hours worked by the finishers either. All right? So these were the carpenters, and these were the finishers. Now, it's asking us for 2 more inequalities, and these are the ones that often get missed the most. We've talked about them before, but we have to try and see, does it make sense to have negative values? Can I have negative hours worked for these carpenters? Can I have the negative amount of chairs that we build? And we can't. So we're going to say that C has to be greater than or equal to 0. And we're going to also say that the D has to be greater than or equal to 0. And so we would traditionally write all of those over here. Because we're making a video, I'm just going to skip that. But we would want to make sure we build, and maybe I'll just do it this way, some kind of set builder notation to show that all 4 of these are the constraints to our inequality. All right. Then we have to graph them. All right, so now we're going to try and graph them. And I'm just going to go back here for a moment to try and find the intercepts. Okay, if we graph, let's imagine that the C is the x-axis and that the D represents our y-axis. So as I'm graphing these and as I'm looking at the intercepts, I am truly using C's as if it's on the x-axis and D as if it's on the y-axis. I hope that makes sense. So the x-intercept, again, is using the C, is going to be something comma 0, where I take 8,000 and I divide it by 4 to get 2,000. The y-intercept for that first one, I get 0, comma, and I'm solving 8D to 8,000, which is 1,000. Then we're going to do that for inequality 2 as well, right? 2C is 1,300, so 1,300 divided by 2 is 650. So 650, comma 0. And the y-intercept, if I put 0 in for that C part, I got to solve 1D is 1,300, or we get 1,300. And then we've got to remember we have those as well. So as we try to graph those, let's go ahead and let's just try and take all of this information over to the next slide. I'm going to just try and list it down here. Okay, that should work. All right, so all we're working with as I trying to create my graph is I'm going to create only this way on the y, which we are calling the D values, and only this way on the x, which we're calling our C values, okay, our C's. And we have to try and maybe adjust a little bit. And so I'm going to count by 100s. 1, 2, 3, 4. This would be, say, 500, 6, 7, 8, 9, 1,000, or 1,000 going this way. And then I'm going to count by, I don't know, 200 going this way. So 2, 4, 6, 8. So this one would be 1,000 right there. 2, 4, 6, 8, and this one right here would be 2,000. So we have to make sure that we adjust those scales accordingly. All right. Inequality 1, which I'm going to try and draw here in blue. All All right, inequality number 1 has an x-intercept of 2,000 and a y-intercept of 1,000. Now, we said it could equal 8,000 exactly, so we are definitely going to connect those two with a solid line, because any point on there will satisfy that constraint. Then the green line, the second inequality. Oh, I'm sorry, we still have to shade this one, right? We still have to shade. Is the point 0, 0 a solution to the top inequality? 0 plus 0 is greater or less than 8,000. That's true, so we would shade underneath the blue line, under that blue. Then we can go to the green, where we have 65. So what did I count by? Shouldn't be 65. That should have been 650, Mr. Goodacre. I'm sorry if I confused you on the last slide. 650. So 200, 400, 650, we're going to say is like somewhere right in there. The y-intercept 0, 13, so 1,000, 11, 12, 1,300 is right in there, meaning we can connect those also with a solid line. Okay, so we've got that nice little solid line. If I check 0, 0, 0 plus 0 is less than 1,300, we are also shading under the green line. Our last two inequalities, we have to be greater than 0 on the x or for the c's, and we have to be greater than 0 on the y's or the d's. So in a sense, our feasible region is this region, just in red. We are stopping right there, okay? So that's our feasible region. That's what will work in both of the inequalities. So now we need to use all of that information to try and find or list out those vertices, okay? Try and list out all of those vertices, the four corners, if you will. So 0, 0. Over here is 650. Got to remember that 0, 650, comma 0. Up here on top is 0, comma 1,000. And then there's a point of intersection right here, which is 200, comma 900. And if you needed to find that, you could go into Desmos, type the equations, see where they intersect. 200, comma 900. So we've got all of these vertices. Then what happens is we need to try and plug them into a formula to see how much money they make. So suppose that a company earns a profit of $15 for every chair and $20 for every desk. The profit equation would become $15 times every C value, every chair I make, plus $20 times every desk I make. All right, so everything that we did up to this point was what we did in the first part of our chapter. Now we're getting into the linear programming part, trying to use the vertices to maximize, in this sense, our inequalities, or maximize the profit. We're trying to see which one of those vertices will give us the greatest profit possible. Clearly 0, 0. If I make 0 of each, I'm not going to get any money. Okay? But remember, as we test these are going to be C's and these are going to be D's right here. And this is where I'm going to stop the video, because I'm going to have you try and see if you can't plug in the vertices using this profit formula to see which one of the vertices truly gives you the most profit, the greatest amount of money. We will continue working on this and practice using different computer programs the rest of this week. But if you have questions, please make sure that you reach out. Otherwise, folks, we'll see you next time. Stay safe.